Hello and welcome to the channel. Today I want to make a short lecture on this topic of designing a ranking function for ads auction. This is a very common topic and I receive a lot of questions about how do we choose the ranking function, what goes into the design of this ranking function. And I think at this point this is simply a common knowledge and I don't even have a definitive link. I don't know who figured it out first, but I have this paper here which I know explains this topic pretty well. It is by Alexei Chervonenkis and some colleagues from Yandex. And Alexei Chervonenkis here is the same Chervonenkis that is famous for the VC dimension, a concept from the machine learning theory. So I will not follow the paper. I will just use my own notation and I will try to explain the concepts here. And the mathematical tools we are going to use are going to be simply the constraint optimization within equality constraints, basic Lagrange multiplier theory, and also the envelope theorem. So let's start by understanding the setting of this problem. So let's say we have the typical ads auctions where we have a series of auctions numbered by a small k, the small letter k, and we have the auctions going from number 1 to number capital K. In each of these auctions, we have some participants, some bidders, and these bidders, they come with the bid of ith participant. We're going to use the small letter I to number the participants. The bid could be auction specific, so we will have this index K specifying the auction number. And then this bidder comes with two additional properties. One property is going to be the click-through rate, CI. And then the other property is going to be, we will call this property relevance, the relevance I. And in particular, we are interested in the case where the highly relevant items, let's say this relevance is in the range from 0 to 1. And we really want to present, we really want to choose the ads in a way that would keep the relevance at a certain level. And sometimes it's useful to use the quantity that is the inverse of or the reciprocal of the relevance, which I will call damage. So di is going to be simply 1 minus ri. So when we have a highly relevant item really close to 1, the damage is essentially 0. And then when we have extremely relevant item with relevance close to 0, we have a very high damage close to 1. Now, we want to make a certain simplification of the problem. And the way it is going to work is going to be like this. In every auction, we are going to have the ad slots. And there is going to be some number of this ad slots in every auction. We should think about it as just a typical sponsored search results or promoted listings results. And each of the slots is going to be specified, it's going to be characterized by the capital X, which is the effective size of the slot. Effective size. And we are going to always assume that the slots in the auction are arranged in the descending order of the effective sizes. So x1 is larger than x2, and the x2 is larger than x3, larger or equals than x2, larger or equals than x3, and so forth. And we will make the separability assumption that is going to be the assumption that will lead to a major simplification and which would allow us to get a really easy and simple understanding. And it works like this. If we decide to place the ith ad into the jth slot, the CTR, the click-through rate of this ith in the j slot is going to be given simply by multiplying the click-through rate of the ith candidate by the effective size of the slot. So we will see later that this simplification will allow us to come up with a simple ranking rule for the auction. And if we don't do this, the allocation rule is going to be more complex than just simply ranking. Okay? And similar, we will assume for the damage that the damage of placing the ith candidate into the jth slot is also going to be given by the same expression. So we will take the damage of the ith candidate multiplied by the effective size of the slot j. In the following, we will use the assignment variables, which are going to be small xij's, and these are from the set of 0 and 1. So if we decided to assign the ith candidate to the j slot, the small xij is going to be equal to 1, and otherwise it's going to be 0. Now we want to start formulating the optimization problem that we want to solve. And the optimization problem is going to look like this. We want to maximize the expected revenue, or sometimes it is called value. We want to maximize this value over all allocation variables in all auctions. And this is going to be equal to the sum over all auctions, over all possible assignments of I and j, of the assignment variable ijk. Then we would use the bid of I in the auction k. But we also assume that this is a click auction, so we are only going to charge when the click happens. So we need to put in the expected click-through rate, which is going to be ci xj. And all these quantities are auction specific. And this goes, the sum goes over all auctions and over all possible ith and j's allocations. Okay, so this is the thing that we want to maximize, but we also want to put a constraint. We want to say that, well, we want the allocation to have at most a certain damage. So then the damage of the allocation xijk, again, this depends on all the assignment variables, is going to be the sum, again, over k, I, j, xij, and now here we put di and xj. Okay. So this is the assumption that the damage is also proportional to the intrinsic damage of the item, of the candidate, of the ad, multiplied by the effective size of the slot. And we want to constrain this. So we want to require that this total damage is less than a certain maximum allowed damage d. Okay, so currently this optimization problem is an integer optimization problem because we have this assignment variables as the discrete set. So we have only the choices between of 1 or 0. And the typical thing to do here to simplify this optimization problem is to assume the linear relaxation of this problem. The linear relaxation basically says that instead of considering discrete values, we want to consider continuous variables bounded between 0 and 1. So the xij relaxed variables are going to be from the interval from 0 to 1. And when we do this linear relaxation, we can see that this optimization problem is, in fact, just simply a linear programming problem. So now we can start solving this linear programming problem using the standard approach of Lagrange multipliers. So to write it out, first we need to write the Lagrangian in a canonical form, which is we want to put the objective as if we were minimizing this objective. And then we also need to put the constraints in the canonical form. And by that I mean that we need to move this to the side and make the constraint that is less or equals than 0. So just to not get confused here, we want to have the inequality constraint to be expressed in this way. And then since we want to, for Lagrangian formulation, we want to minimize, we will also use the minus sign here. So we have minus sum over kij, xij, bicixj, all of them with the k index here. K is the number of the auction. And we want to put the Lagrange multiplier lambda. And then we want to multiply this by the constraint expression. So this is kij, xij, di, xj, all of them with the index k minus d. Okay, so here we have the Lagrangian of this problem. And let me actually explicitly write out what this Lagrangian depends on. It depends on all of the allocation variables and the Lagrange multiplier. And the typical approach here would be to use the Lagrangian to derive the dual function. Or I would rather say a dual optimization problem. So the dual optimization problem for inequality constraint is derived from the Lagrangian by taking an unconstrained minimum. So we need to we will denote this dual objective as g of lambda. And it's going to be the minimum over xij of the Lagrangian. And the constraint for the dual optimization problem is that the Lagrangian multiplier is larger or equals than 0. Okay, so now let's take a look at the problem of minimizing the Lagrangian here with respect to the allocation variables. Well, we can see that actually we can group these terms together. We can pull out the assignment variables. We can also pull the common effective slot sizes. And then we will have something like this. So let's rewrite the Lagrangian here in this way. It's going to be a minus sum of kij, xij, xj, bici, and here we are going to group these things together and note the sign. Here we had the minus, here we had the plus. So this is going to give us the minus lambda di. And then the remaining term is going to be minus lambda capital D, but for the purposes of minimizing this expression with respect to xij's, this is what we want to do to derive the dual function. this thing is constant with respect to xijk. Okay, so now we want simply to minimize this thing. And given that there is a minus sign, what we really want to do is we really want to maximize, let me rewrite it just like this. We just want to maximize this expression, xjk bi ci minus lambda di of k. So we really want to maximize this. And this is a very easy maximization problem. First thing that we want to note here is that this is a sum of independent optimization problem. Sum of independent optimizations over auctions. Each optimization problem for individual auction is independent of the rest. So we have this Cij, xj, bi, ci minus lambda di. We want to maximize, and I dropped the k because this problem is the same in every auction. So how do we? Yes, we need to keep the sum over ith and jth. So how do we maximize something like this? How do we choose the allocations to maximize this sum? And really, we already have the answer here. This is the expression of the ranking function that we are looking for. Ranking function or ranking score. And first thing that we can note here is that, well, really we don't really want to allocate any of the candidate if this ranking function is negative, because this is just going to not ever give us more value for the optimization function. So from here, we immediately see that, first of all, we need to discard and not allocate anyone that is any candidate that does not meet the condition of being non-negative or positive. And this is the threshold property. So given a fixed lambda, like choose lambda and compute this score function. Let me give it a name. It's called S of I and lambda. So first step in this optimization inside a single auction would be to remove all the candidates which do not meet the threshold. Okay. And the second step is going to be to sort them. Just basically sort by S, I, and lambda in the descending order. And assign the largest one to the largest effective slot with the largest effective size. And then take the second one and assign it to the second largest slot, and so on. This is possible because of this simplification that we made, the separability assumption that gave us this very specific structure of multiplying here. In a more general situation, that would be the problem of finding the optimal bipartite matching. But with this additional simplification of separable click-through rates and the separable damages, we can solve this problem just by sorting and just by assigning in the sorted order. The result of this sorting is that we actually found the optimal allocation variables xij given the lambda, and we did this for every auction k. So now in every auction k, given the lambda, we know the optimal allocation variables, And just to repeat myself again, quickly, discard everyone that does not pass the threshold, sort them using the ranking function, and assign in the descending order of effective slot sizes. Now we can write out using this, okay, lambda star. Again, remember what lambda star means. Lambda star means this is the optimal assignment. And now we can write out the dual optimization problem that is going to be a single dimensional optimization with respect to the lambda variable. So the only thing that remains to be done is to find the value of lambda. Okay, let's see. So the g of lambda now is going to be equal to minus, and we just need to rewrite, essentially we need to rewrite the Lagrangian, but replace the x here. Let me highlight it here. We just need to replace this with an optimal x with a star. So it's going to be minus sum of kij xijk star. And now it depends on the lambda. Then we have bicixj. Actually, I can even like pull the whole ranking function here. So we have xj and cibi minus lambda di minus lambda d. And the dual optimization problem now is to maximize g of lambda, constrained that the lambda is larger or equal to 0. Well, I want to rewrite this. I just want to get rid of the minus signs here. So I'm going to minimize the minus g of lambda, which is going to be minimize the sum of xij star of lambda, xj, cibi minus lambda di. And yeah, sorry, I forgot to put the index k everywhere except for lambda. Lambda is a single number. K, and k plus lambda d. And this is where we can solve this one-dimensional optimization problem using the envelope theorem. The envelope theorem says that this is just going to be a very small reminder what is the envelope theorem and what does it do. So the envelope theorem really says this. Let's say we have the some function f of x and t, and the value function of t is going to be given by maximizing with respect to x of f of x of t. Then when so this is like given the t, for every given t, there's going to be some maximization problem that is going to be solved with respect to x. And just to show you that this is exactly what we've just done with the Lagrangian, we had, in the place of t, we had the lambda. So lambda was given to us. And then in response to that, we would find the optimal allocations x, I, j, k. Okay, so this is very, very similar, exactly the same as this simplified formulation here. And then when we are interested in the derivative of t, oh yeah, let me put it like this. So yeah, so we can also say that when we executed this optimization with respect to x, we found the x star, and this is going to be f of x star of t and t. Okay. So now when we are interested in finding the derivative of v, the idea here is going to be, okay, let's use the expression for the derivative of a combined function. So this is going to be f derivative of f with respect to t, which is the explicit part. And then we also need to go through this combination. So we need to do the f derivative with respect to x star t and t. And now we also need to take the derivative of optimal x with respect to t. And what essentially the envelope theorem says is that we can really discard this part. Because when we are optimizing with respect to x, we are, like in the simplest case, we are going to just set the derivative of f with respect to x to 0. This is the condition for the maximum. And this is the reason that this term vanishes. But in fact, the envelope theorem says that this works even for non-differentiable functions with respect to x. It could be really an arbitrary optimization, like a choice optimization. So there could be this variable x could actually be a discrete choice, and still this term is going to vanish. So how are we going to use this theorem for our particular optimization problem here? Well, we want to minimize the minus g of lambda with respect to lambda. How are we going to do it? We need to take the derivative with respect to lambda, and we are going to essentially assume that this is a constant, that this optimization variable, which depend on the lambdas, when taking the derivatives, we don't need to think about them. We can assume that for the purposes of taking the derivative, these are actually constants. This is the consequence of the envelope theorem. So let's take the derivative. The j, okay, we want to minimize, but it doesn't really matter. J prime lambda. And since this is a constant now, the only term that depends on lambda is this, and we have the sum of kij xij star depends on lambda, in each k star depends on lambda. Then we have xj di k minus d. And this should be equal to 0. This is the condition for the optimum here. And really, this thing simply says that we need just to find the lambda that would just make this go to 0. And also remember that we had the constraint of lambda. So this is how we actually get this is the way to derive the KKT condition. The KKT condition says that either lambda is 0 or the constraint is 0. K star ij of lambda xjk dik minus d is 0. Really, either lambda is 0 or this constraint is 0. So essentially, we found everything that we wanted to find. This is the end of this derivation. So let me just rephrase again what we found. We found that with this separability assumption, with this additional simplification of the separability assumption, we can, in each auction, we can solve the problem by using the ranking function here. This is the ranking function. And using this ranking function with the given value of lambda, we would find the optimal assignment given the lambda. And then we will just use that optimal assignment in this expression to see if, so basically, if we have the violation of the constraint, we need to move the lambda in a way that the constraint is going to be satisfied, and it needs to be satisfied exactly. Well, in practice, we are not going to have this satisfied exactly. We are going to have this satisfied approximately. There are many reasons for this. In practice, okay, let me spell it out. In practice, we use the ranking function, which is going to be this bi ci minus lambda di, and we are going to threshold on it. So we are only going to keep the participants which are passing the threshold. And then we are going to rank them according to this ranking function, and we're going to assign them to the slots. And for the choice of lambda, we're just going to scan the lambda. And we are just going to find the lambda that approximately gives us the constraint, the result that is like just a little bit below the damage that we allow to ourselves. And this is it. Maybe one additional note, a note on the auction. So far, we haven't really used the fact that this is the auction. And typically the auctions, they are not only concerned with allocation, they are not only concerned with ranking the functions, but they also need to come up with the pricing. And the ranking function in this auction is a linear function of the bid. Linear function of the bid. So the bid enters here as the in the linear fashion. And this is known as the affine maximizer option. And I'm not going to do it here, but it's very, very easy to derive the formulas for the GSP or the VCG auction. Basically, we just, for the GSP, it's very, very simple. Actually, I can spell it out that, well, we just need to equalize the first guy with the second guy, C2 minus lambda D2. And now we need to find the smallest b that is going to make this equal. And this is going to be the b that gives this equality. This is going to be the GSP price. And for the VCG auction, the computation is a little bit more involved. We need to spell out the whole allocation curve. But again, with linear function, spelling out the whole allocation curve is actually very, very easy. And then we can find all the points on the allocation curve where we have a change in ranking, and then we need to sum the contributions of that. So I'm not going to do it here today. Thank you so much for the listening, and see you next time. Bye-bye.